Hi, I'm Avi Punjabi, and today I will be reporting Spitzer infrared observations of B2615 Ophiuchus. Starting off with some background questions, what is Spitzer? Spitzer is a space telescope, one of four main extraterrestrial telescopes we use to better understand the universe. Probably the most famous would be the Hubble Space Telescope, which looks at ultraviolet and visible light data. There is also the Compton Space Telescope, which looks at gamma rays, and the Chandrasekhar X-ray Observatory, which looks at X-rays. And finally, of course, the Spitzer, as you can see in this photo here provided by NASA, that looks at infrared rays of light. Another background question, what is spectroscopy? Spectroscopy is the study of the emission and absorption of electromagnetic radiation, which in this case is measured in flux. As you can see by this image provided by the AAVSO, because the energy levels of electrons are quantized, meaning they're at specific levels and nothing in between, the wavelengths that these emission lines are occurring at is actually characteristic of specific elements. So seeing what wavelength emission lines occur at can tell you what element is present in the system. This image only shows us with visible light, as that's what we can see, but it also applies to infrared light as well as many others. Finally, what is V2615 Ophiuchus? It is a classical nova, much like this image here provided by the ISRO. As you can see, there's a cool red giant that is transferring some of its matter to a hot, much denser white dwarf. But on top of mass transfer, there is also lots of matter that gets ejected from the system entirely with the stellar winds. This matter is a variety of things, including individual elements, namely heavier elements, but also dust, such as silicates, carbon, amorphous carbon, and even hydrocarbons. So my overall question is, did dust formation, with what I said previously, occur in V2615 Ophiuchus? My methodology for this project was to first plot the flux versus the wavelength to see when the emission lines, or where the emission lines were occurring. I then fit and subtracted the continuum, and then fit the emission lines with various fits, and then determined properties from those fits. Then finally, to see the overall system conditions of the system at the time of observation, I compared it with light curve data. That last step is critical as it allows you to really see if conditions were sufficient for dust formation to even have occurred. Now, verbally, that can be pretty confusing. So visually, it looks like this. The first step you can see here, where I have the flux in Janskis and the wavelength in microns. The red is simply just uncertainty. You can already kind of visually see the giant spikes, which are emission lines, but this will be further quantized. Then I have the steps 2 and 3, where I fit this blue continuum with this red line and subtracted it to make this flat green line. This red line was originally a black body fit. A black body is an ideal body that emits zero of its own radiation, and thus would be perfectly representative of the system that you are looking at. If the continuum was fit with a black body fit, then it would be a telltale sign that dust formation did occur. However, I found that a black body fit did not accurately fit the data, and instead went with fitting it with a 12th order Chebyshev fit. A 12th order Chebyshev fit is just a generally good way of fitting any sort of curve, but there is no extra astrophysical conclusion I can really determine from it. Upon flattening the line by continuum subtraction, identifying the emission lines is pretty easy and looks like this. This emission line specifically is this big giant one here. As you can see, there are multiple fits here, namely a Gaussian, Lorentz, and Voigt fits. Gaussian fits are just simple statistical fits where every piece of data is a set amount of standard deviations away from the mean. Lorentz fits are a bit more complicated because they take into account Doppler broadening, which is where emission lines are fatter or thinner at their base because of the Doppler effect, which is very similar to when an ambulance rushes towards you and goes up in frequency and then goes down as it goes away. Very similar process, except with light instead of sound. I then plotted the residuals as well as a reduced chi-squared test to determine how well each fit represented the data. As was the case with this one and many other emission lines, the Voigt fit was the most accurate. This is because Voigt fits not only take into account Doppler broadening like the Lorentz fit, but also takes into account Gaussian mathematics with the standard deviations. My results for this were as follows. Quantitative results are right here. This mostly served the purpose of verifying conclusions that were shown by previous studies, namely the Minari 2008 study which argued dust formation did occur. Here I plotted the wavelength that five emission lines were recorded at, and then the ID of that, the previously observed wavelength in a vacuum, as well as the transition that atom itself is going through to emit that emission line. These three pieces of data were taken from the Peter Van Hoof database. The integrated line flux was then calculated, as well as the expansion velocities. The latter two were derived from the Gaussian, Lorentz, and Voigt fits. Note, these five emission lines are the only ones listed because these are the five emission lines that occurred in both observation A and B of my Spitzer observations. My qualitative observations were where I really answered the question of whether or not dust formation occurred. As you can see here, there are the five emission lines that I showed before in my table. These five are the ones from observation A, and these five from observation B. A telltale sign of dust formation is when the left end, the higher energy bluer wavelengths are at a lower amplitude, at a lower flux than the right wavelengths. You can kind of see this with this emission line right here. However, this is one with very high uncertainty. As you can see with the rest of them, none of them really exhibit that sort of asymmetry. In terms of how quickly they go up, they're all very, very symmetric and really don't suggest that dust formation occurred at all, which is in line with the fact that a black body fit did not fit the continuum data. So what conclusions can we draw from this? Upon comparing this with light curve data, like I said before, the Minari article actually did argue that dust formation occurred, which is in contrast to a 2007 Moody study that said dust formation did occur. The Minari data argued that dust formation could not have occurred because there was no dip in the light curve. The only time it conceded that dust formation could have occurred was around the 4,270 HJD mark, which is seen right here and seen even easier right here. You see a smooth decline with a considerable dip and then return to that smooth decline. This means that high ionization was just sweeping through all of the ejecta, and then that ejecta is more energized, more reactive, and dust can form easier. This was not observed at either points of observation A or observation B, and thus heavily suggests that dust formation did not occur. That being said, this light curve data was pulled from two places: the Minari study that I talked about earlier, as well as the Sunny SB database. And then in this graph, I just put them together. However, the Sunny SB database, as you can probably notice, has a lot less data points than this and is a lot less reliable. Observation A and B of my Spitzer data both occur during the Sunny SB study. So seeing that there is no visible dip in the light curve can be kind of misleading because there might just be not enough data. So my implications for this, as I said before, with my light curve data, it doesn't really suggest either way whether or not dust formation occurred. But the fact that a black body did not fit the continuum data and the emission lines themselves did not exhibit much asymmetry, I concluded that dust formation did not occur in V2615 Ophiuchus. However, it is very possible that it still did, just at a different time. As such, I recommend that further study is done, particularly in the visible light curve range, to better understand the long-term evolution of V2615 Ophiuchus. Additionally, there were several other lines that simply could not be fit. For some, this was simply because they were falsely detected by the Python program and were not actually emission lines. But for others, namely around the 11.3 micron range, they could not be fit because they were too wide, not just at the basis, which would be because of Doppler broadening, but throughout the entire thing. This is a characteristic sign that it is not an atom emitting that emission line, but rather a lattice of atoms in a molecule. This molecule would then emit an emission line via oscillations in that lattice itself, which would give you a much wider wave, a much wider emission line with a lower amplitude as the energy is more dispersed. One of these molecules could be a polycyclic aromatic hydrocarbon, which are of particular interest, PHs for short, which are of particular interest because they are organic molecules, they are hydrocarbons. If they were present in the system, that would really help with better understanding how organic molecules were first created in the universe, how they moved around in the universe, and then eventually how they reached us to make us. However, upon trying to fit this 11.3 micron emission line with an algorithm called PAH fit, there were several technical difficulties that arose because the algorithm was originally made in IDL, which requires a license to use, and my data analysis was one in Python. So as such, I also recommend further study, preferably in IDL with PAH fit to better understand whether or not PAHs were in the system. So any questions?
Amanda, I have my hand up. May I ask a question, please?
Are you able to hear me?
Yes.
Excellent. So what I'll do first is I have 3 oral defense questions, and then we'll get to your question. Okay, Professor Chick? All right. So Avi, my first question for you is, how did you determine which results generated by your research method were most important in identifying your new understanding?
Right, so a big help with that was previous literature, specifically both the Rudy article and the Minari article. The Rudy article studied infrared observations of this system. So seeing what infrared data it looked at specifically, and then seeing what conclusions it reached from that data was very helpful because I had my own infrared data that I could look at the same data points for and then find my own conclusions for. Additionally, the Minari data drew its conclusions from light curve data like the one that I showed you before. So seeing that same light curve data, as well as a little bit more from the Sunny SB database, and then drawing the conclusions via the same methodology that Minari used was very helpful for me to determine not only what methods to use, but understand why those methods work and how they work.
Excellent, thank you. My next question for you, Avi, is how do your findings provide direction for new research in the field? You did allude to that, but I was wondering if you could say more about that.
Right, so a big thing about classical novae is that they are believed to be how heavier elements as well as hydrocarbons and organic matter like silicates and stuff came throughout the universe and were originally created there and then moved around in the universe, which are very critical to forming planets, which are what we live on today. Understanding better what a classical nova looks like when it creates specific heavier elements such as iron, which was observed in my system, or PAHs, which were not necessarily observed but could be, would be very helpful to understanding the evolution of the early universe to the universe we see today.
And my last question for you is, how did you handle, excuse me, I just read that one. How do your findings provide, I just asked you about the future research, yes?
Yeah.
I apologize. So how did you handle uncertainty in your research process?
So a big part of that was actually help from my mentor, Dr. Woodward. When I was working on trying to get the black body to fit the data, there were several parameters that I had to mess with to try to be absolutely certain that the black body didn't fit the data. This took me about 6 hours in total of just fiddling with parameters, which was a very menial, repetitive task and was really, really discouraging when I realized that ultimately a black body just did not fit the data. Additionally, this was very, very early in my research process. So I was still very unfamiliar with understanding that sometimes, especially in research, when something doesn't work, it can tell you just as much, if not more, about a system. This was when Dr. Woodward came up to me and I realized that because the black body fit did not work, that actually told me that dust formation probably didn't occur, which actually was convenient in that it lined up with the rest of my observations. So understanding that sometimes when something doesn't work, that can actually be very helpful in research, which isn't necessarily the case with many other things that I've experienced in school, was very new to me and very helpful.
Outstanding. That actually summarizes the end of the formal part of this process. So I'm going to hit stop recording now.